In this problem, we're to find the force in each of the 5 members that make up this truss. So, giving them names now, we want FAB. We will want the force in member BC, CD, AD, and the force in BD. Before we begin, we can do a quick inspection to see if we definitely have any zero force members. Looking at the 4 pins, A and C are supports, so we won't consider them. B has an external force, D has an external force, so we won't consider them. So by our rule of identifying certain zero force members, we can't see any for certain. That doesn't mean that there aren't any, we just can't rule them in at the moment. Yeah, so to find these 5 forces in the members, we want to first look at the truss and the supports it has. It has a pin at A and a roller at C. So this will be a statically determinate structure. As we can tell, there's going to be 3 support forces when we draw the external picture. This means that I recommend that the first free body diagram we draw to solve this will be the external one so that we can solve for the supports. So first free body diagram, and they will all follow this XY coordinate system. So free body diagram 1, I will draw the external structure. So I need to include the external forces, and I need the dimensions of everything. We have this applied load of 4 kilonewtons that is 2 meters from A to B and B to C. We have this applied force of 3 kilonewtons. And then we have the supports at A and C. We are removing the pins, so we need to know what happens at point A, and we're removing the ground at C, so we need to know what does C do, what does the ground do to point C. All right, so let's start with A, the pin. We are going to model that as an AX component and an AY component. And at C, we're going to have the normal force. We are told that theta is 30 degrees. So we know that the force is going to be 30 degrees, but it's normal to the surface, so it's 30 degrees from the vertical. And I'll call that C. So externally, this is the free body diagram with the applied loads and with the supports. And we can use this to find AX, AY, and C. We already knew going into this there were 3 unknowns we would have from the 3 components of support. So first we can solve those, and then we can start looking internally at what's happening. So we'll again kind of go between our equations, our solving, and our free body diagram as we go. So first equation coming from the first free body diagram. And actually here, I'm going to start with the sum of moments. And I'll do it at point A where we have the pin, which is typical, because I know that that's going to eliminate 2 of my unknowns, and C is going to be the only unknown in this equation. The order doesn't really matter, but I know that equation 1 will immediately give me the value for C. So taking the moment around point A, and again, this is picture 1, AX and AY are eliminated. We're going to have negative 4 times 2 from the 4 kilonewton load that is 2 meters away and causing a clockwise rotation. So again, counterclockwise positive here, and I will specify Z is coming out. We are going to have also clockwise, so negative, a 3 kilonewton force times 1.5 meters. Everything here will be in kilonewtons, and meters is what I'm going to use for the base unit. And now I have to consider the vertical component of C, which is actually going to cause a counterclockwise, so positive force. So the vertical component will be C cosine 30, and it has a distance of 4 from A. So this is the force I'm considering. because the horizontal component we can see is going to pass through A and therefore not contribute to the moment around point A. So just that vertical force, C cosine the adjacent side times 30 times its distance of 4. And we can actually solve that right away. I'll come back to the solve step though. So 1, we have already a solvable piece. Now we can move on and write a second equilibrium equation. And now let's do the x direction in picture 1. We are going to have all of AX plus the 3 kilonewtons from the applied load minus C sine 30 degrees. By solving equation 1, we'll know what C is. We'll be able to find AX. I'll just do a solve step after this set of equations is written, though. And the y direction, all of AY minus the 4 kilonewton applied load plus C cosine 30 degrees will be in the positive y direction. All right, so let's look at a solve step here. So equation 1, we can solve that, and we can find that C is going to be a positive 3.61 kilonewtons, and in the direction that we assumed. And that has to be positive because the ground can only push on our roller. In equation 2, now that we know the value of C, we can find that AX is going to be a negative 1.2 kilonewton. It's negative. We assumed it was pointing to the right. It actually points to the left. And using our knowledge of the value of C in equation 3 will give us the value for AY is a 0.875 kilonewtons. It's positive, so our assumption of up is correct. So for these external support forces, I do want to include their proper directions next to it, because when I go to my pin diagrams next, I do want to draw these in the correct direction when they appear. So we've solved our supports. Now we can actually go inside and start to solve for the unknown forces. So in our find, we actually haven't found anything we ultimately need to find yet. All right, we have our supports, so now we can see what pin diagrams would we like. We have A, B, C, D to choose from. I'm going to go with method of joints here because I do want the force in every one of the members. So I'm going to start with pins that only have 2 members attached to them if possible. So B and D, I would rather not start with because they have 3 members each. However, C, let's say, only has 2. So I'm going to start my first pin diagram at C, and this will be particle equilibrium. And because I already know the support at C, this will only have 2 unknowns on it. So let's start with that support reaction, which we know is 30 degrees from the vertical. And at this point, I will put in its value, since we calculated it, to be 3.61 kilonewtons. Now for the members, assuming tension, I will have the force in BC, and I will have the force in CD. And FCD is going off at an angle. If I look, the horizontal is 2, the vertical is 1.5. That's actually a 3-4-5 triangle. So the FCD is at a different angle than that 3.61. We want to keep that in mind. Okay, so 2 unknowns, and that's why I chose to start at C. So I can get 2 equations out of this particle equilibrium free body diagram. I will start by summing forces in the y direction, actually, because there's only going to be 1 unknown. So sum of forces y in picture C. I will have here the vertical component of that applied load, so 3.61, times the vertical component is cosine of 30 degrees, plus 3/5 times FCD. And those are both positive. So I started there because equation 4 has only one unknown in it at this time. And in the x direction then, I will solve that one next. I will have minus 3.61 sine of 30 minus all of FBC is completely in the negative x direction, minus 4/5 FCD. So equation 4 and equation 5, I can now solve for those. Equation 4 has only currently one thing I don't know, which is FCD, and I can solve for that. FCD, I get a negative 5.21 kilonewtons. Negative means that it's in compression. Note for the pins, like the support reactions, those do not, tension and compression do not apply to those, but for these internal forces, the tension or compression does apply. So negative, again, if we assume tension positive, negative will mean compression, positive will mean tension. And we can then use equation 5 to find FBC. FBC is going to be positive 2.36 kilonewtons, and then that is in tension. So two things we ultimately wanted to solve. We have CD and BC. So CD and BC, I will mark here just to keep track of that. All right, so we can only get two equations. We got those two equations for the two unknowns from C. Now we can move on and pick another pin to draw because there's still three unknowns that we need to find, which means we need at least three more equations to do that. So we can move on and go to A or B or D. Now looking at B, attached to it are three members, but now one of them we know. So I'm going to choose to do B next. We could have done A or D for that matter, but I'm going to go with B. I like that there's no angles involved, so it's just going to be pretty quick to draw this one and solve it. One external force is acting, which I'll copy exactly, 4 kilonewtons. Now the members attached to it. Again, I always want to assume tension, so for consistency. So FBC, notice it's in the opposite direction as it was in the previous picture because it's in tension in both pictures. It's pulling on B and pulling on C. So I assumed tension in picture C. I must assume that in picture B. I'm ignoring right now the fact that I know its numerical value. The only time I'll put in numerical values in my pictures is going to be for those supports like I did in picture C. So for now, I'm leaving everything in variable form. So FAB to the left, assuming tension, and FBD up, assuming tension there. So picture B, two things I don't already know the values for. In the equation step, I'll put 6 over here so we can see it. Summing forces in the x direction, let's start there. We have FBC minus FAB. And in the y direction, we have the negative 4 plus FBD. So two equations out of that. In the solve step, 6, since we already know BC is 2.36 from previously, now I'll substitute that in. So equation 6, the only thing left I don't know at this point is FAB. So FAB must also be a positive 2.36. We're in kilonewton, so it too is in tension. And then in equation 7, FBD is the only thing I don't know. It's the only unknown in this equation. FBD, I'm going to get a positive 4 kilonewtons, so it too is in tension. FAB, FBD, I now know. FAB is known, FBD is known. So only one remaining member that I need to find the force in. I'll need one more equation at least to solve this. So I need to pick a picture that's going to have FAD in it. I have now at this point used my point C and my point B. I have pictures of both of those. Just mark it to keep track. So I could do A or D. Now note, I can do a pin diagram at A and D. I can generate 4 equations. However, only one more equation I generate will be linearly independent, as we're going to see. So let's use A. It's going to be just a little bit less work. So A will be the last picture that we'll draw here. So drawing A as the next free body diagram. At point A, we have the support, which we solve for, AX and AY. Again, we know the numerical values of that support. I will put them in as numbers and in the right direction. AX was negative 1.2, which meant it pointed to the left. So I'm going to put it in the correct direction, left, 1.2 kilonewtons. And AY, we also know from that very first free body diagram, we found to be 0.875 up. All right, so those support reactions are in the picture now, in the correct directions with their correct values. I only do that with the supports. The members, I'm just going to leave as variables and then plug in the values later. I have AB, assuming tension, so FAB to the right, and FAD. And FAD is that 3, 4, 5 triangle, 4, 3, and 5. 4 is the horizontal, 3 is the vertical. So in A, that is what I have left. So I can use that to get 2 more equations. I'm going to look in the y direction first because that's the direction that still has my one remaining unknown. In the y, I will have 0.875 from the reaction, the support, plus 3/5 FAD. And I can get equation 9, but we'll see what happens here. In the x direction in A, I will have negative 1.2 plus FAB plus 4/5 FAB. In equation 8, the only unknown is FAD in this equation, so I can solve for it. FAD will come out to a negative 1.46 kilonewtons, so it will be in compression. Marking this, so FAD, that was the last thing we were asked to find. We now know it. But notice there's still equation 9. We didn't use it yet. We didn't technically need to, but let's see just what happens. In equation 9, FAB, well, I already know that from equation 6, and I made a error here, that's FAD. And FAD I now just found from equation 8. So we're in static equilibrium. This equation must be true because the sum of forces must equal 0. If I put into equation 9 2.36 for FAB, and if I put in negative 1.46 for FAD, with maybe a little bit of rounding error, equation 9, we are going to get 0 equals, and the right-hand side should be 0 or something very close to 0. So notice it's just a true statement, and it must be true if we're in static equilibrium. So the equation 9 turned out to not be another linearly independent equation. Only 8 of our equations were linearly independent. Only 8 of them gave us new information. 9 turned out to be redundant, although still true. And notice we did not make the free body diagram for pin D. We did not need to solve for our unknowns, but the 2 equations that came out of that by this point would also have been redundant and should give us 0 equals 0 or something very, very close due to maybe just some rounding errors. So drawing D and checking that to make sure those equations is true is not necessarily a bad idea to check your work to make sure everything's consistent. However, there's no new unknowns being introduced in those two extra equations. So in the end, we found all 5 of the unknowns we wanted, which were the forces in each of the 5 members. We started with the external picture because it was statically determinate, so we could figure out the reactions at A and C. Once we found out those, then we drew the pin diagrams, starting with what I thought would be the easiest place to start, which was C, because only 2 members were attached to it, and then working our way from right to left, more or less, to solve for our unknowns. The order, again, doesn't really matter because as long as we have enough linearly independent equations for the number of unknowns we have, we know we have a solvable system, and then we can go and solve it. So here we did, and we got our resulting 5 forces that we were interested in.